Okay, in this video we're going to look at basic 2D projectile motion. This is part one. I'll do some more complicated problems. But the basic projectile motion that we see here is an object is flying forward at 75 meters per second or any sort of velocity, and something's going to be dropped. But there's no VIY, and the initial Y velocity is 0. So there's no initial Y velocity. It's just strictly horizontal. It's not thrown up. It's not thrown down. This plane's going straight forward. And this object, which is also at the time of the flight, is going the same speed. So it's not something else. This object right here should also have a Vx of 75 meters per second. And then we have some sort of distance it's going to fall from. So here's the components of projectile motion, a basic projectile horizontal motion problem. Before we get into it a little bit too far, let's go through some of the basics of projectile motion. So if we have a projectile we throw at an angle and it's going to follow this trajectory right here, which is a parabola, its ending velocity will be the same as its starting velocity. So if this was 30 meters per second, its velocity would be 30 meters per second, but it's going to be in this direction. So whatever this direction was, it'll be a different direction, but it's going to be the same velocity at the very end. And in the middle, it's going to have the minimal velocity. It's going to be the least out of any of these. And in order to see that, you need to take a look at the next slide. And here is a common drawing that we see here. Rather than having the actual speed, often we'll break it into its components. They'll be going so far forward and so far up. So we have an x velocity and a y velocity. And as the object goes up, this y velocity gets smaller and smaller and smaller to the point where it's nothing. And then it gets bigger, but in a downward direction, bigger and bigger. But that's because the acceleration due to gravity equals 10 meters per second squared downwards. So it's changing this velocity the whole time by 10 meters per second at the top of the flight. Once again, this is always going to be the case. No matter where in the flight it is, acceleration is 10 meters per second squared downwards. But there's nothing, once again, this is the ideal conditions, assume there's no air resistance. There's nothing stopping. There's nothing slowing down or speeding up the x-axis. So the x-axis stays the same. The velocity in the x-axis stays the same. And we call this independent. So no matter what's happening to the y, the x is doing something of its own. So if this was 10 meters per, let's go ahead and use 12 so it doesn't sound like it's this number. 12 meters per second velocity. Over here it's 12 meters per second. Over here it's 12 meters per second. Over here it's 12 meters per second. Only thing I know, let me just throw in an arbitrary number. If this is the Vy was 40 meters per second upwards, well, that's going to slow down, slow down, slow down. At the top, I know that it's going to have a velocity of, now this would be initial or final in most problems, and this would be, so this Vy would probably be initial velocity, and this would, if you're concerned with how high something goes at the top of the flight, its y-axis is, velocity is 0 meters per second. So this is a Vx. These are all Vx's all the way over through here. This is all the Vx's. And every single one of these would be 12 meters per second. 12 meters per second. I've done all this. I might as well keep it going. 12 meters per second. 12 meters per second. So now it should be obvious that every one of these Vx's is 12 meters per second. It did not get affected by the 10 meters per second squared down. It kept on going. It was like it was rolling the whole time forward. It never changed. Its Vx was 12 meters per second. But the y went to 0, and then it kept on, as the acceleration kept on kicking in, never changed. The acceleration here is still 10 meters per second squared. This caused that velocity at the very end, the Vy was going to be 40 meters per second, but downward. So the magnitude is still going to be 40 meters per second. But the direction of that, so the Vy here is going to be whatever that it was at the beginning, and then the end is going to be exactly the same. It sounds like the same question as this. If I keep on going back, this is the actual velocity. This is where I'm not concerned with up or forward. It would end up being that in this angle, the speed would be the same. But here it's just really talking about the y component. So it's kind of the same thing. If you make a mistake, a lot of students probably make that get that question right on the test because they just know it's opposite, but it's kind of different. Okay, so here's a basic problem. A plane drops a package from a height of 50 meters while traveling at a speed of 75 meters per second. So draw a picture. There's my plane, and it is flying at 50 meters. So sorry, no, that's 75 meters per second. So I'm going to make a separate x and y givens list. And this is important because we cannot mix these two together. The only thing we know is when this object hits the ground, it will be done in the x-axis and y-axis. So the only thing that's not considered independent, we're not considered with any sort of bouncing or anything that goes on after the package hits the ground. The time it hits the ground, it is done going forward. It's going to end up going forward, and it hits the ground exactly at the same time. And so that's going to be the connection that ties these two together. So if we can find one of these times, we'll be able to use that in the other axis. But the x-axis is not affected by gravity, so it's going to have this constant motion. This is the only problem you'll use in the x-axis because gravity is not affecting it. Whereas the y-axis, gravity will be affecting it. So we're going to be going to any of these, knowing that our acceleration due to gravity in the y-axis, a equals 10 meters per second squared. Now, the specialized equations would say this is g, but we might as well not memorize any new equations. We're going to be using one of these equations right here. This object's going to be falling. Also, another thing to note here is the object is falling from rest in the y-axis. It's going only forward in this problem. And so it's going only forward at 75 meters per second, but it's not going anything. The VIY is going to be 0 meters per second. It's starting from rest. It's just, in the y-axis, this object's going to act like it's just falling faster and faster and faster, whereas in the x-axis, this object is going to be going further at the same speed the whole time. So next step. Okay, so what else do we have? Oh, height of 50 meters. Okay, there we go. We have x equals, which in this case would probably be a y, but since I'm going with these equations, I'm calling it x. You probably put y there. Is 50 meters. And so how long does it take to fall 50 meters starting from rest at an acceleration of 10 meters per second squared? If we can solve for this, we can use this over here. Well, let's finish off our givens. The Vx, the speed in the x-axis, was 75 meters per second. In order to do this problem, the only thing we need left over, well, actually what we're trying to solve for, downrange. Have you ever heard the term downrange? We're talking about just the ground or just the forward. So downrange, another way of saying downrange is going to be x, or displacement in the x-axis. We're not concerned with this. We're just concerned with how far forward is it from where it landed. So we have everything we need to solve for x. Let's go ahead and solve for this. Which equation has x, or vi and x, and a and a t in it? And it's going to be this one right here. In order to use this to make it simpler so it's not quadratic formula, you want to realize one fact. If vi is equal to 0, so let me just go ahead and erase that. The vi, this is my vi. If vi is equal to 0, then this whole thing cancels out. If vi equals 0, x equals to 1/2 at squared. And if I want to get rid of a multiplied by 1/2, I'm going to multiply by 2. Next, if I want to get rid of an a, I'm going to divide by a. And next, if I want to get rid of a squared, I'm going to take the square root of everything here. I already got rid of that. So I'm going to take the square root of everything here. And a simplified version of this equation right here. Time equals the square root of 2x over a. Anytime the initial velocity is 0, you can use this equation right here to solve for time if we know a distance. And so it's just a simplified equation and this is on some equation sheets as square root of 2y over g. So that's just the same things. T equals square root of 2y over g. If you look at the projectile motion equation, the section of our equation sheet, if you're in my class, this is what it is, what it says. So you can skip straight to it if it's a horizontal motion problem where VIY is 0. So square root of 2 times the y, which is 50, over the 10. These are both downwards. These are downwards. And what I tell my class is if you put the vectors in the downward direction, it's going to fall 50 meters. It's going to go accelerate down 50 meters. Well, if I was solving for like a final velocity, I don't have to use positives and negatives. I'm going to just go ahead and use positives, and my positive represents down. So if it was a vector at the end, if I was solving for like a VF, I would have the same vector direction because it would my answer if my answer ended up positive, and I'd have the opposite direction if my answer ended up negative. So these are both positive, so I'm not going to use negative and complicate things. I'm going to keep it as a positive 50 and a positive 10, which would have canceled out anyways. So we get 2 times 50 equals, divided by 10 equals, and I get right now it's 10, but that's not, I need to take the square root of 10. And so the square root of that is 3.16 seconds. So this is 3.16 seconds, which means that it is done going, it's done falling at 3.16 seconds. So now I'm concerned with, well, how far, if it's going forward at 75 meters per second and I give it 3.1 seconds, how far is it going to travel? That's what this is right here. It's traveling a constant rate. So the way that this equation is rearranged, v equals x over t, it rearranges to x. X is on top. I can keep it there. I want to multiply out the t. X equals v times t. The velocity is 75 meters per second. The time it's allowed to go is 75 meters per second. So it's going to be a little more than 3 times that 75 is 3.1 seconds. 16 seconds. So 3.16 seconds. And I get 75 times 3.16 equals 237 meters. So this package is going to land, this one right here, 237 meters downrange. And that's where I would want, if I had a target, if this was a target problem, where would I put the target? I would put it 237 meters from where the package was dropped. Okay, another way that these problems are often asked, let's go ahead and draw the picture again. Here, I'm given a plane. My plane looks, I'm tired. Been here for a long time. It's Friday. My plane looks a little funky. Okay, the plane, a package lands. So here I hear about the package lands 87 meters downrange. So this is my X, and this is going to be in my, once again, it's projectile motion, so we'll have separate X and Y givens list with T being the target. Or the target value you want to solve for that connects the two. That's the only thing that's going to be the same on both of these. We call these X and Y velocities and everything else independent because of that fact. We can't mix these, and that's why I have separate givens lists. So my X equals 87 meters. Going to land 87 meters downrange from where it was released while traveling at a speed of 53 meters per second. So it's traveling with a Vx of the plane was traveling horizontally 53 meters per second. So this is my Vx equals 53 meters per second. And then just some of the y givens, it's going to be dropped. The question here is how high was the plane? So once again, you probably use y, but I'm going with these equations right here. I'm not trying to give any new equations. So how high was the plane? That is what the question is. And we know that it's accelerating through the sky at 10 meters per second squared down. So once again, we're going to use positive values unless we see an up arrow in our givens list. And we know that it was dropped. So our VI, I won't put Y here because I'm using X there, but this should be a Y, this should be a VIY. VI is going to be 0. It's dropped from a velocity in the Y axis of 0. And if we can find the time, we can find the x. And where are we going to find the time? We're going to find the time right here using this x-axis. So v equals x over t. This vx is just a specialized v. It's just v. X equals, multiply out the t. We're left off with x equals tv or vt. And that's never mind, let's start that over again. We're solving for t. V equals x over t. We want to get t alone. So we're gonna multiply out the t, leaving t over here. Now we have to divide out the v so that we can get v away from this t. And so this ends up being, so second round's the charm, this ends up being t equals x over v. and x is 87. The velocity is 53 meters per second. So how long would it take for you to go 87 meters if you're going 53 meters per second? 87 divided by 53 equals 1.64 seconds. So we know this is 1.64 seconds. And therefore, so that's the time it has to go forward. This ball is going to be following this path right here. When it is done going forward, which is 1.64 seconds later, it will be done falling. So that's also 1.64 seconds. So that doesn't ruin the fact that the X and Y are independent. It's just that they hit at that point in time, and that's when it's done falling. So the Y-axis acts like falling, while the X-axis acts like it's just going forward at a constant velocity. And now I have X, A, V, V, I, and T. X, A, V, I, T. Here we go. Everything I need. X equals VIT plus 1/2 AT squared. X equals VI, which is 0, times T, which is 1.64, plus 1/2 times A, which is 10, times T, which is 1.64 squared. Only the T is squared. This cancels out. 0 times anything is 0. And I like to type things in backwards in my calculator. 1.64 squared equals, I like to type it in parts, times 10 equals, times 0.5, or just divided by 2, or times 1/2, whatever way you want to type it in. And I get 13.448, I'll just go ahead and say 45 meters. So this package was dropped when the plane was 13.5 meters above the ground. It's a little dangerous for that plane. And hopefully this helps.